Hi, my name is Manish Gupta, and in this video, I'm going to talk about the recently released T5 Gemma models. They are encoder-decoder Gemma models. So let's get started and understand how are these models trained and how do they perform. Okay. So how are these T5 Gemma models trained? T5 Gemma models are actually encoder-decoder LLMs, and therefore they are basically prefixed with T5. So in fact, so T5, as you know, is a very popular encoder-decoder architecture, but most recent large language models are decoder only. So these authors basically wanted to ask this question that, hey, can LLMs be encoder-decoder based, and can they perform as well as decoder-only large language models, right? So that is why they trained T5 Gemma. They follow the T5 architecture in that sense, is encoder-decoder architecture, but they have been initialized, using the Gemma decoder-only models. Basically, they are adapted from decoder-only models, where adaptation basically means initializing the parameters. As you can see in this picture, you basically take a decoder-only model, which basically contains the feed-forward layer and also the self-attention with the rotary position embeddings. You take and then you use it to initialize the T5 architecture-based encoder-decoder models, where the feed-forward layer basically is used both on the encoder and the decoder side to initialize. Self-attention layer is basically also used to initialize the encoder and the self-attention on the decoder side, except that on the encoder side, yes, the forward-only attention is converted to bidirectional self-attention, right? The cross-attention piece is the only thing that remains uninitialized in some ways. In this work, they basically train T5 models of the T5 Gemma models of different sizes. As you can see, they train 2 billion, 9 billion, small, base, large, and extra large kind of models. 2 billion models are 26 layers, 9 billion models, 42 layers, and so on, right? So small models are 8 layers deep as well. Small, base, large, and extra large are of the same size as the T5 the original T5 models. Now, of course, using these T5 models, they adapt and come up with encoder-decoder T5 Gemma models. So if it's a 2 billion Gemma model that is used to initialize a T5 Gemma model, the T5 Gemma model would be 4 billion in size because it's 2 billion for encoder and 2 billion for decoder in that senses. Plus embedding parameters, which are not mentioned here, right? Similarly, if you take the 9 billion Gemma model, which actually is like 8.3 billion, 8.3 billion plus 8.3 billion would be 16.6 billion plus like 0.1 billion for embedding parameters in that senses. So basically you get like a 16.7 billion, encoder decoder Gemma model. So a T5 Gemma model. So T5 Gemma models are written like this: 2 billion, 2 billion, meaning 4 billion parameters in size, 9 billion, 9 billion, meaning 18 billion parameters in size, and so on, right? So therefore, there are these four other small, base, large, and extra large sized T5 Gemma models as well. Okay. Now, these are all balanced T5 Gemma models in the sense that the encoder and the decoder follow the same number of layers, but they also train unbalanced T5 Gemma models where, just one of them, a 9 billion, 2 billion checkpoint where the encoder is 9 billion in size, but the decoder is 2 billion in size. Okay. Now, for the balanced Gemma models, which are basically all of these, the cross attention is initialized from the self attention of the decoder only model itself. But for unbalanced Gemma model, which is basically this 9 billion, 2 billion checkpoint, right? They initialize the cross attention weights essentially from scratch, and they fine tune these weights for the first k steps as a warm up in pre-training part. Okay, so the k is basically 1,000. So for the first 1,000 steps, you basically fine tune just these cross attention weights, keeping all other weights frozen, right? And then after these 1,000 steps are done, you basically train or you fine tune all the model parameters. You don't freeze anything. Okay. So what is observed, and while training, obviously they need to use pre-training data. So pre-training and instruction tuning data, they do, supervised fine tuning. They also do RLHF and so on. All of that data is taken from Gemma 2. So the pre-training recipe, all the training recipe is typically from Gemma 2 in that sense. Okay. Pre-training is done using two different loss functions. One of them is prefix language modeling, which is typically very similar to causal language modeling, except for the prefix part here. So remember, this is an encoder-decoder model. So it's not exactly causal language modeling, it's prefix language modeling in that senses, right? But with knowledge distillation. So not just that they initialize parameters from decoder-only models, but they also do knowledge distillation. Okay, that's one pre-training loss. They also pre-train using another loss, which is called as the UL2 loss, which comes from the UL2 paper. So what they found is that the DeFi Gemma models pre-trained with prefix LM loss do better for generative tasks, but the UL2 models actually perform better for encoder representation tasks, specifically all the tasks in the superglue benchmark that they experiment with. Okay. So that's about how these models are trained. Now let's see how do these models perform. Okay, how do these DeFi Gemma models perform? So the first picture that you see here is basically x-axis number of tokens and y-axis is the pre-training score. So this particular picture basically shows that the models really get pre-trained very fast. So as you see, with very little number of tokens, so they train for 2 trillion tokens overall, right? But for with very little number of tokens of pre-training, the model already basically saturates in terms of their pre-training loss, right? So these three curves are for the three different models: pre-train 2 billion, 2 billion, 9 billion, 2 billion, 9 billion, 9 billion, and you also see those dotted curves. These are for the Gemma to 2 billion checkpoint and the Gemma to 9 billion checkpoint. So you see, basically, the Gemma 2 models basically took quite some time to reach that level of pre-training loss. But then the T5 Gemma models, obviously, because they benefit from adaptation, from initialization of the weights, they basically reach their pre-training loss thresholds much faster. Okay. Now, what is also observed, so what is this picture? This picture basically shows you how do the T5 Gemma models perform on pre-training data sets. So pre-training is evaluated on different data sets and instruction tuning on different data sets. So you take the pre-trained model, you instruction tune it. So there are two different data sets. So don't compare the pre-training score with the instruction tuning score, but this is evaluated over like 10 different data sets. Is also again over 10 different data sets. Okay. But rows basically show you the size of these models. Gemma 2 basically is the original Gemma 2 model, and plus prefix LM is the T5 Gemma with prefix LM pre-training. This is T5 Gemma with UL2 pre-training loss, right? And what you observe is that typically with these pre-training losses, whether it is prefix LM or the UL2 losses, for these larger checkpoints, you basically obtain better results, better pre-training score. Okay. You also get better results after instruction tuning. If you compare, Gemma to instruction tuned and RLHF model gets like 39, but you see the increase is significant, 46.4 on the 2 billion checkpoint. Now, obviously, on the larger checkpoint, you get, 59.6 becomes 64.5. Okay, the numbers in the brackets here are basically for RLHF models, while the numbers outside the brackets are instruction tuned models only. So net, the thing is that even if you do zero shot, evaluation, but with the pre-trained model or with the instruction tuned model, you observe that T5 Gemma models are actually better than the Gemma models. Okay, that's about the larger sizes. But if you look at the smaller sizes, typically you will find that the pre-trained model is actually not as good as the original Gemma 2 model itself. So the pre-trained T5 Gemma model is not as good as the Gemma 2 model itself. But even the smaller sized models, if you instruction tune them, even they become better. You see, so instruction tuning of smaller models also works when you are doing T5 Gemma kind of pre-training. In that T5 kind of T5 Gemma kind of pre-training and instruction tuning. So encoder-decoder large language models actually can give you better results compared to decoder-only models. Obviously, in this paper they only compare with Gemma models. This needs to be seen with other kinds of models if encoder-decoder kind of pre-training and instruction tuning is better than decoder-only models. Okay. Now, what they also do is to take these pre-trained checkpoints, or the instruction tune checkpoints, RLHF checkpoints, and so on, and also fine-tune them specifically on the training sets of the superglue data, right? So these are results on the right side of the fine-tuned models. Okay, in that sense, is fine-tuned on superglue data sets. Okay. So again, what you observe is that these fine-tuned checkpoints, especially the instruction-tuned fine-tuned checkpoint, right? That's actually much better with the UL2 loss. So with the UL2 loss, you see, the original Gemma 2 model was giving you 86.2, 2 billion checkpoint gives you 90.5. Okay. Similarly, XL T5 model was giving you 69.2, but this is like a significant boost of like many points, right? 87 is the new score. Okay. So you see, you should think about it like this. You were able to get like 86.2 with a 2 billion checkpoint. And now suddenly the XL model, which is basically fairly small, XL model is like 1.6 billion, right? In that senses, overall, it gives you 87, much better. Okay, so that's that. Now, if you compare these models, the top part, right? if you compare in terms of pre-training score, instruction tuning score, or even the superglue based fine-tuning score, compare the encoder-decoder model with the decoder-only model with different amounts of inference latency and inference flops, right, at inference time. So basically, you might feel like, hey, Gemma 2 billion model is just 2 billion, but T5 Gemma 2 billion is 4 billion, right? How about inference latency? I mean, obviously, these T5 Gemma models are better than comparable Gemma models. But do they also give you similar latency or lesser latency? So what is observed is that if you compare with inference flops and pre-training score, inference flops and accuracy in terms of instruction tuning score or superglue score, you observe that the encoder-decoder models have a better Pareto front, compared to the decoder-only models. Basically, they always give you better trade-off between the accuracy versus inference latency, whether you compare after pre-training or instruction tuning or fine-tuning. Okay. So specifically for fine tuning, when you fine tune these models, right, on classification kind of superglue tasks, the way the fine tuning is done is you take the instruction tuned model or the pre-trained model, and you basically stack a task specific head on the representation of the last token in the encoder, right, for encoder decoder T5 Gemma models. But if you are working with, let's say, just the Gemma model and you want to compare superglue performance, right, you basically stack a task specific head on the last token of the decoder because it doesn't have an encoder anyway, right? And then you fine tune all the parameters on the training set. So that is how the superglue fine tuning was done. Okay. Okay. So in short, in this video, I talked about T5 Gemma models, which have been adapted from the Gemma models themselves. Okay. They basically the authors have released prefix LM as well as UL2 pre-trained and instruction tuned checkpoints of different sizes. Small, base, large, and XL, as well as 9 billion and 2 billion checkpoints, as well as the T5 Gemma 9 billion, 2 billion unbalanced checkpoint. Okay. The overall observation is that the encoder-decoder T5 Gemma large language models would outperform the decoder-only Gemma LLMs of similar sizes, especially after the instruction tuning, right? While maintaining the same latencies, Okay. So that's it for this video. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.